Thanks for coming to this Nuclear Energy Innovation Bites event. I'm Dr. Harry Cools. I'm a lecturer in structural integrity at the University of Bristol. And this event is part of the Faculty of Engineering Research Showcase, which is ongoing throughout this week. I'll post a link to some of the other events that are happening in the chat in a moment, so you can have a look at some of those and see if anything else piques your interest. We will be recording this event, so please just be aware of that. And in this event, we'll have 3 speakers talking about different little bits of research, bits of applied research in the kind of nuclear area. This is all research that's coordinated by the Southwest Nuclear Hub. And the Hub is an organisation that we have here at Bristol that brings together industry, together with academia and government as well, and really sort of acts as a hub for both fostering collaboration and kind of coordinating applied research in the nuclear sphere. So without further ado, I'm going to introduce our first speaker. So our first speaker is Dr. Abdullah Al Mamun. He's a senior research associate in the solid mechanics research group, the same research group as I work in. And he's going to be talking about structural integrity and lifing of nuclear components and basically materials engineering research that we do in the nuclear area. And a lot of Abdullah's work is associated with the EDF High Temperature Centre and coordinated through the hub. So thanks very much, Abdullah, and we look forward to hearing your talk. We'll have questions at the end of each one of these talks, so please hold your questions till the end. Thank you.
Thanks, Harry, for the introduction, and thank you all for attending this seminar. So I'm currently the EDF Fellow in High Temperature Nuclear Structural Integrity. So Bristol is part of EDF's High Temperature Center, where our group's research is on materials. And our aim is to improve the life assessment procedure of the nuclear power plant that EDF use, and thus maximizing the life of the nuclear power plants that UK has currently. So as you are aware that nuclear has and still playing an important role to the energy mix of the UK, but the contribution of nuclear is going to drastically reduce over the next few years. And this is because all these plants that were built in the 70s and 80s are close to their retirement age, and some of those are going to retire in the next 5 to 10 years. So both from economic point of view, environmental point of view, it makes sense to maximize the life of this plant until those can run safely. And that will eventually reduce the unit cost of the nuclear power, which is one of the main arguments against new nuclear build, that it's too expensive to build and too expensive to produce the nuclear energy. And we are working towards that goal. So I'll start with a very simple question of what limits the life of a nuclear power plant. So this figure, it shows a schematic of a conventional nuclear power plant. And as you can see, many of the components of these plants operate in harsh service conditions. For example, there is high temperature up to 650 degrees Celsius. There is corrosive environment there. There is oxidation, there is fatigue, and all sort of different deformation mechanism. And it is actually the deformation and degradation of the materials in the plant over time that limits the life of the plant. And one of the particular deformation mechanism, which is a bit tricky to estimate, is the creep deformation. So in simple words, creep happens when you put a piece of metal, for example, at high temperature, about 40% of its melting temperature. And then if you put a small amount of load, which won't cause any permanent deformation instantly, but if you keep that temperature and that small amount of load for a very long time, the material deform and degrade and starts to crack and fail and all sort of thing. And it is a bit more tricky to estimate how long a component will last in terms of creep, because it is time dependent deformation, and we need to estimate for a long time, maybe like 45, 50, 60 years of the plant life. So it is, I'll give a simple example. For example, this steam pipe through which the steam flow, high pressure and high temperature steam. So when it flows through the pipe, it creates this high temperature into the material of the pipe, which probably made of steel. And of course, there is this steam pressure. So it just creates this condition for creep, and it deforms over time. But if it was just deforming like that, so if it was like a steady state, like this constant pressure and constant temperature, then it would be much more simpler for us to predict how long the pipe is going to last. So we could like just simulate that, like take a piece of a sample from this pipe and put it in a furnace and put it dead weight and see how long it's going to last, and maybe then derive some empirical relation to extrapolate it, like that. But in real life scenario, it's much more complicated. For example, when the plant first start up, when first time the steam is going through this pipe, the inside of the pipe gets heated up pretty quickly and it tries to expand, but the outside remains still remain cold, so it cannot expand. So it puts a lot of plastic deformation, for example, compressive stress during shutdown as well, vice versa. And maybe there is a weld in the pipe which has some additional stress we call residual stress in the pipe. And then there is this microstructural variation, and creep is very sensitive to this microstructural variation. So this all makes it like much more difficult to predict simply with a, like empirical relations or a simple test like the one showing on the right-hand side figure. So what we do to address this challenge is to take a bottom-up approach in our group. We thought maybe it's more important for us to understand the deformation mechanisms inside the material. So for example, how that plastic deformation is affecting the creep deformation, but not just in a component scale, but in a grain scale, in a much, much smaller scale. And then we can, build a model of this material. And then we can apply some sort of constitutive law, which gives us the deformation within a grain, and then that can be built up onto specimen and then to component and so on. So for that, we used a special modeling technique called crystal plasticity finite element model. So in simple words, as you know, any crystalline material or any metal is a form of thousands or millions of crystal or grain. And if we apply a uniform pressure, for example, in this cube, the deformation in the individual grains will be different depending upon those orientation, those size, shape, neighboring grains, and so on. And what crystal plasticity does, if I can define a constitutive law for deformation occurring in a particular grain, and then if I run the model for a volume of like for thousands of grains, then it can give me like an average response of my volume. By the same time, it can give me the local response. So for example, I can see where is the stress concentration happening in my material, or I can see if a particular type of loading is causing more stress concentration than the other, and that sort of intricate details. And the good thing about it is that we can include all the information, all the variety, like for example, microstructural variety in this initial volume. We can introduce residual stress and all that sort of thing occurring in the material, which dictates the deformation. So the biggest challenge for this type of modeling is to know whether our model is performing correctly. We can build up this model, we have some assumption, we can have all these parameters and so on, but how do you know that this model is performing accurately and correctly? So for that, we use a few different things because it is a mesoscale model. So we are building this from grain length scale. So only doing an experiment at the lab where we get like average response from our specimen is not enough. But it gives us this macroscopic deformation with which we can compare our model prediction and see if it's predicting it accurately. But we also need to know whether the grain response that we are getting in our model are actually a true representative of what's happening inside the material. And for that, we need to go one scale down. So I'll talk about each of these stages briefly. So for mechanical or macroscopic deformation, we have this amazing facility here in Bristol. We have this high temperature mechanical testing machines where like we have this creep machine where we can do that like a dead load type of simple creep test at temperature. But we also have this really sophisticated mechanical tester where we can simulate these different loading conditions that this material experience in the nuclear power plant, for example. So this has this high temperature furnace, and there is a variety of loading and variety of rate and variety of temperature that we can apply. So this gives us the way to validate our model using this macroscopic data. But for so when we want to validate our model with this grain scale data, so it's not possible in any local lab. So for that, we use this national synchrotron and neutron diffraction facilities in ICES. We have a long-standing relation with them. And what these techniques offer is, so they have like very high energy X-ray or neutron, which can penetrate through the material. For example, this small sample can penetrate, can give you the information of the deformation of your grain with respect to their orientation and how those are related to the loading axis of my sample. So this gives us a really amazing and unique way, like to compare our model's prediction of local deformation of how grains are deforming to experimental observation of the local deformation. And we use other technique, for example, advanced microstructure based technique in cooperation with the Interface Analysis Center at Bristol, where we can track the different stages of evolution of microstructure during the creep deformation, how it is evolving for like different types of loading, different types of constraint. For example, we can use weld materials. We can look at like all sort of different material, and this is like another way to combine with our crystal plasticity model to get the certainty that what the model is predicting is actually a true representation of the deformation and damage occurring into the material. And this work that we are doing both in terms of modeling and experiment is not limited only to nuclear fission or EDF energy, but we are applying this to a wide variety of other applications. For example, nuclear fission is a big thing for our group at the moment, because also the material in the fusion reactor goes through this high temperature and different types of loading. So creep fatigue is important. The material is different, but we can adapt both modeling and experimental technique to that. We are working with additive manufacturing, again, because in additive manufacturing, the grains are formed in a particular orientation. And it is very important to take into account the effect of texture and residual stress into it. So we are working on that again with our technique and with our model. And we are also looking at the future. So, of course, many of these plants will be closed. The fission plants will be closed in next 5 to 10 years. So, but there is many opportunities to take forward this expertise that you have built working on this fission application. So, for example, on the digital twin, so there is a drive, not just only to predict the deformation occurring in the plant condition, but also we need to know, like the manufacturing route of those components and whether our model can capture those correctly, so that we can actually create a digital representation of the components just entering the plant, and then like we can track the deformation and damage. That gives like a much more robust prediction of the life of these components that's going to be into the nuclear new build. And of course, there's a lot more opportunity in the fusion with new material, with higher temperature, and so on. Nuclear new build, there is one being built at Hinkley Point C, and of course there is other opportunities with drive in advanced manufacturing in the UK at the moment. So in summary, so our materials research currently is supporting this UK's nuclear plant life extension, as well as the research into nuclear new build. We have access to a state-of-the-art modeling and experimental tools, both in our lab, in national facilities, and also in the international central facilities. And the expertise that we are developing from this work is not just limited to nuclear fission, but we are applying to other areas like advanced manufacturing, fusion, etc. So that's all from me. Thank you very much for hearing. If you have any question, I'll be available.
That's great. Thank you very much, Abdullah. Okay, so we'll open the floor up to any questions. You can use the Q&A function, which is at the bottom of the screen if you're if you're in Zoom. So in the meantime, while questions are getting started, I've got a question for you, Abdullah, if you don't mind. Yeah. So I think there's some really interesting materials research going on there, but what are the challenges involved in translating that into things that you can use in a plant context? crystal plasticity. It's really interesting. It's, to see how things deform at the grain scale. But how can we use that? What are the challenges?
Yeah, so that's a very good question. So one of the challenges, so we are at the moment, given our computational power and experimental facilities, we are looking at small scale. So we are looking at small specimen. The X-ray has certain energy which can penetrate only a small amount of material, and the model can take much longer to run if the material is too big. So the biggest challenge is, like moving from this small scale specimen to the component level. And there is some work that we are doing at the moment, for example, going outside the finite element method, but using a method called fast Fourier transform, which runs much faster. So it may be possible in next couple of years, to run a component in crystal plasticity, and then you can, pick the hotspot of deformation, damage, that sort of thing. So that's like one of the biggest challenges, translating the scale.
Wow, yeah, that's impressive though. If you can run a component scale simulation like that, that would be really good.
Yeah.
Okay, good. Okay, so there aren't any other open questions in the Q&A. If anyone has any questions for that, then yeah, do type them in or type them in chat. But I think what we'll do now then is we'll move on to the next panelist, who is Sam White. So thank you, Abdullah, by the way.
No problem.
Yeah, so we'll move on to the next speaker, who's Sam White. So Sam's a third-year PhD student in the physics department, actually. And his work really centers around robotics, so robotic waste inspection in nuclear, sorting and segregation of waste. His work also uses the National Nuclear User Facility, of which Bristol is a member. And I'll post a link or two relating to that in the chat as Sam is speaking, in case anyone here is interested in using NNUF facilities. So at Bristol, we have part of the hot cell robotics or hot robotics facility, and also the active nano mapping facility as part of NNUF as well. Anyway, I'm going to hand over to Sam now to talk about his research in robotics. Yeah, take it away, Sam.
Thank you for the introduction, Harry. Yes, so today I'm going to be talking about robotics for nuclear decommissioning and the new NNUF Hot Robotics Facility that we have available in Bristol. So just to quickly introduce myself, given this is an online talk, my name is Sam. I'm a PhD student at the University of Bristol and the Southwest Nuclear Hub. My PhD is co-sponsored by KUKA Robotics, and I research the characterization of nuclear waste using robotic manipulators. I'm also a member of the NNUF Hot Robotics team that we have here in Bristol. So to give a quick presentation outline, I'm going to begin with an introduction to the NNUF Hot Robotics Facility. I'll then dive into a sort and segregation case study where I'll describe my system setup and give you a video demonstration of the system that I'm using to help sort through the endless piles of nuclear waste that we have here in the UK. So a bit of a whistle-stop tour, but without further ado, let's dive in. So the National Nuclear User Facility, or NNUF as I've referred to it up until this point, is a large conglomerate of different universities and research facilities across the country. There's some 20 facilities ranging from everything from synchrotron sources to thin film research, all the way to nuclear decommissioning robotic systems. And that is what the Hot Robotics deals with. So Hot Robotics is divided up into 4 different facilities. There's the NNL, the National Nuclear Laboratory in Cumbria. There's the University of Manchester facility. There's RACE in Oxford. And there's also us at the University of Bristol. And the primary objective of the facility is to provide a test bed for lots of different robotic equipment, which is available for people to hire, both from academia and the research world. So in Bristol, we have the facility at Fenswood Farm, which is located just outside of Bristol. And at Fenswood Farm, we have a wide variety of robotic systems available for hire, as well as sensory systems. So to give a quick summary of some of the kit that you can hire via NNUF at Bristol, we have various drones the DJI range of drones, the M600 for heavy payloads, and the Mavic 2 for smaller, more rapid flights. We have a variety of ground-based vehicles, such as the Leo rover, which is a wheeled robot, and the Super Droid, which is a tracked robot. We have a variety of KUKA arms, which I'm going to talk more about later, but we have available the KUKA Iwa arm, as well as an industrial robot arm, the KUKA KR120. And as well, we have an A1 robot dog, which is a very cool quadruped robot, which is all available to hire, as I say. So we also have a range of sensory technology available as well. We have the Vanta Olympus XRF, which is a handheld XRF device capable of material characterization. We have an offering of radiation detectors from Chromac. We've got the TN15, which is a neutron detector, and we have a GR1 and Sigma, which are gamma radiation detectors. We've got the Velodyne LiDAR system, which is excellent for mapping environments such as rooms. And it should also be noted that we have available a number of radioactive sources, which can be used for different testing purposes. And just to mention, this is all available via the User Access Scheme Fund, which is actually free to researchers up until 2023. So until 23, you can hire for free, and that includes your travel and subsistence costs. Actually, the University of Leeds have already taken us up on a few sensor systems, which they're hoping to take out to the New Forest. So it's not just that you can come to us and use our facilities, but you can also take some of the equipment away. If you want to find out more about that, there's plenty of information on our website, and also there is a newsletter which I'd encourage you to sign up to for the latest information. So I want to get now into a bit of my own research. I've been looking at the sort and segregation of nuclear waste, and I've been able to do this thanks to a lot of the NNUF equipment that we have in Bristol. So just to begin with, I think before we start sorting waste, we actually need to understand exactly what nuclear waste is. Well, nuclear waste is not just the nuclear fuel that is used to power reactors, but it can be everything and anything that may come up as part of decommissioning processes. This could be steel offcuts such as pipework. It could be soil or brickwork, rubble, the air-fed suits such as the image shown in the bottom left there, in bottom right, sorry, or even the fuel cladding. So the containment structure of the fuel when it goes into the reactor. Which you can see in more detail on the image on the top right. And our goal in the UK is, I mean, a lot of it has materialized from the legacy facilities and, you know, the early days of nuclear when we were not so cautious about how we stored waste. So we have these large storage vaults, such as the one on the left image there, which is the Berkeley active waste vault, where all of this waste was just kind of collected together very randomly. And so what we want to do is extract it from those vaults, sort through it, and then reorganize it into safe long-term disposal as far as a geological disposal facility shown on the right. And just so you're aware, because it comes up in later on in my talk, there are many different classes of nuclear waste which range in danger to human health in essence. But it's all characterized on the basis of activity per unit mass. So we need to understand the radioactivity of the object and the mass of the object to be able to sort it. So that brings me on to my own system setup. So as you can see, I'm using the KUKA LBR Iwa, which was available for hire via NNUF. The key feature of this arm is that it has force torque sensors in each joint, which I'm actually able to use to make mass measurements in situ as we're sorting the waste. You can use the tension to inform yourself of the actual mass of the object. I combine that with a Intel RealSense depth camera, so we have knowledge of what objects are on the table, and then we can give that information to our grasping mechanism, which in this case was the Blue Robotics Newton 2-finger gripper, which is ideal for this purpose as it is designed to be used underwater. So it's actually waterproof so it could easily be washed down for decontamination purposes. I also used a Chromec Sigma micro gamma spectrometer, again available through NNUF, in order to facilitate the radiometric data that I would need to sort my objects. So that is my system. And to test it, I use the radioactive sources, which are available at our facility, as a test bed to actually see if I could collect each object, characterize it, and then sort it into the waste bins, which are shown on the left. I also had some dummy, similarly sized options that were not radioactive to see if I could sort between them. So I thought about it as a 5-step process. The first step being to survey the table. So we're going to make a radiation map to understand where the dangerous objects are. We're then going to use our vision technology to identify and grasp and collect the objects. We'll perform some gamma spectrometry so we understand exactly how radioactive the object is. We'll then weigh the object so we know then, crucially, that we have the radioactivity and its mass, and then we can sort the object accordingly. So here's my video of that in action. So we can see that the arm begins by performing that radiation map, that initial survey. So the arm comes in and it moves across the scene, collecting radiometric data, and it combines that with the positional data, which is output from the robot arm. So as we sweep across, we have that radiation data, and we can combine it with the positional data in order to make a radiation map. And from that, we can understand exactly where the objects are on the table. It's important to note that actually, if there was no radiation on the table, then the waste could all just be put through some conventional waste stream. So there we see the arm wrap that up, and we get our radiation map, where we can see where the radioactive sources are. Following on from that, we identify the objects using the RealSense camera, and then that can inform our grasping. So the arm comes down and it will pick each object up, where it will then present the object to a gamma spectrometer, the Chromec, in isolation. From there, it knows what isotope it is, and it can quantify the radioactivity or non-radioactivity. We then weigh it using the weighing algorithm I developed, which is accurate to within 40 grams, and then we can dispose of each object accordingly. So the arm will just continue to work through that process. And I should note that this is an early prototype of a potential future system which could fulfill this role at Sellafield or another waste storage plant. So there you see the arm continues, and it will dispense this object. This was a non-radioactive source. I'm just running out of time. So just to wrap up, all the information for NNUF can be found on our website, which I'd encourage you to visit. Hopefully the link's in the chat. And the Hot Robotics website will actually go live officially next year, but I'd encourage you to, later this year, but I'd encourage you to sign up to our newsletter if possible, and you can find out all the latest details of what we're up to. So, thank you very much.
That's great. Thank you very much, Sam. And as before, if anyone has any questions, please either type them in chat or use the Q&A function. In the meantime, I've got a question, if you don't mind, Sam. So something I was thinking about while you were talking there was, I mean, there's quite a lot of things that you could do with this. You've got that gamma spectrometer set up there that you can sort of show an object to. But for the variety of waste forms that have to be dealt with by the UK industry, I mean, what in an ideal world, what would you want to be able to do? I mean, I can think of, say, setting up an XRF, you know, as well as a gamma spectrometer to try and distinguish between, you know, different metals, for instance. Would you throw everything at it, or, you know, what's going to help and what's not going to be so helpful?
Yeah, that's a good question. So actually, more recently, it's funny you should mention XRF. I've been more recently working on XRF for material characterization across our waste piles. And that is crucial, actually, because you do need to understand the material composition before you consign objects to long-term waste stream, because over time, metals, for example, will corrode, and that will induce volume expansions. And you can have adverse reactions with, chlorides and plutonium, for example, which can leave you in big trouble, basically. So that is absolutely crucial. So really, you want to collect as much data as you possibly can about each object ahead of storage.
Okay, thanks. I've got the question from Lars here, who's asking, was this autonomous?
Yes, no, it was entirely autonomous, the system, yes.
Okay.
Even down to we have developed some software which is able to identify isotopes, which unfortunately had to trim down the presentation quite a lot, but we can auto identify isotopes as well.
Okay, great. And there's a question here from Lily, who's asking, Sam, is any sensor or electronic device approved for radiation tolerance, or is it hardened? Have you got to the stage of rad hardening things yet?
Unfortunately, all electronics will eventually fail in radiation, so it's not quite possible. But we have tested the EWA in a radioactive environment, and it appears to fail after 140 grays of dose, which is fairly significant. That's enough to kill 140 people effectively, as morbid as it sounds. So obviously that was just one isolated test. You would want to do some further testing to ensure that was necessarily the case. But it turns out there is a specific component inside which gets damaged, which would be replaceable. So it's more than possible you could have a maintenance facility to deal with this in the long term. Okay,
great. Well, thanks very much, Sam.
Thank you.
We'd better move on now to our third and final speaker, who is Rich Pyle. Rich is a third-year MD student in the RC NDE Centre for Doctoral Training, and he's working on the use of deep learning in non-destructive evaluation for pipeline inspection, not for nuclear applications directly, but with clear nuclear applications as well. So I'm going to hand over to Rich. I will post the RCNDE website link in the chat as you're speaking, Rich, so that people can have a look at that too.
All right, thank you, Harry. So as Harry said, I'm Richard Pyle, third-year NDE student with RCNDE, and I'm going to be talking to you about big data and NDE and unlocking the use of deep learning for non-destructive evaluation. I'll thank at the top here all the other authors on this slide and just mention that, as Harry said, I'm an RCNDE student and Baker Hughes is my sponsor company, so that's the inline pipe inspection aspect of my work. So in this talk, I'll go through the application this work's originally intended for, talk about the aim, which is sizing defects from ultrasonic images, like these here in the top right, as an example, talk about some machine learning terminology and the methods I'm using. So having 6 decibel drop is this baseline method, and then I'm using convolutional neural networks as a machine learning alternative, present some results, and draw some conclusions. So because Baker Hughes does inline pipe inspection for oil pipelines, that's where this data is based around, but pretty much any application where you want from some sensor readings to infer something about your material, this work is applicable, especially if you've got simulations, as I'll come on to that. That's what sort of unlocked this. So inline pipe inspection uses PIGs, or pipeline inspection gauges, that flow through pipelines in the flow of the product. So this would normally be full of oil, and you've got ultrasonic phased arrays in a ring here on the back, and they're used to inspect the pipe for things like corrosion and cracks. They fire ultrasonic plane waves into the structure of the pipe, and then you listen for responses from those corrosions and cracks. And if the online processing detects something, the data is stored, and then later it's looked at by a human to try and decide if that crack or corrosion is significant. I don't have access to one of these, so I've got a test setup that's trying to replicate it, and that's water rather than oil. And I've got my arrays that fire plane waves that travel through the water into a stainless steel plate, and that bounces off defects. So I'm just looking at cracks on the far surface wall, and the sound bounces back off and back to the array. We've got 2 arrays because it's normally a ring, so for each defect you can see it from an array on either side. And I transmit 1 plane wave. We'd love to be able to transmit more to get more field of view, but this thing's traveling along the pipe at roughly 3 or 4 meters per second, so you've really not got time for more than 1 firing. And then listening back on all your transducers, you've got 2 sets of plane wave capture data from any given defect. And to interpret that in a useful way, you can focus it on reception to create images. So you've got to decide on what array path you're going to use, and we found that half skip imaging is the best. So that's the one drawn here, where you've got the sound coming through and it's shear in the plate, bounces off the back wall, hits the defect, comes back to your array. Because we're transmitting in shear, which is where the oscillation is perpendicular to the direction of travel, we can go shear, 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 or we can have a mode conversion off the defect to longitudinal. So that means it's with direction of travel, and we get 4 images. And I guess the key takeaway from this slide is that this is the input to my network here at the bottom. I've got this set of 4 images for all my defects, and from it, I'd like to know how much thickness of pipe we've got left. So how long this defect is. And as I say, I'm trying to use a deep learning approach for this, and the motivation for that generally in all kinds of NDEs, just that there's so much data now and it's so high dimensional that we'd really like to replace or at least augment human data interpretation so we can deal with all this data and be able to just interpret it and reduce the effect of human factors. And I believe, and hopefully I can convince any of you that don't share the opinion, that advanced machine learning methods are a great way of going about this. They've had huge success in all sorts of simulated tasks, similar tasks in the past. So a little bit of machine learning terminology for the uninitiated. It's a subset of analysis and data science, and a subset of artificial intelligence as well. And 2 terms that I've used one of already, and I don't think anyone's quite agreed on definite definitions of these. Most people use shallow and deep learning to mean fairly specific things. Shallow learning says from a data set, you'd have some human selected, handcrafted features that you learn on. You train your algorithm on those to predict something you'd like to know about that data. Whereas deep learning, you skip out that hand selection of features step and you learn from the raw data itself. So for this sort of toy ND example I've pictured, this might be an indication from a defect, and a human might know that the size of this indication, the RMS in the region, and its maximum might be some important parameters. So you only extract those and learn from those how big the original defect was. Whereas deep learning, you feed the full array of sensor readings in. You don't do that hand selection of parameters. Most NDE research in this field has been shallow learning. That's because you need far less training data for this, because it's a much lower dimensional problem. And producing training data for NDE is really expensive because you've got to manufacture all your defects, which can take a long time and cost a lot of money. So part of the novelty of this work is I'm unlocking deep learning by simulating my training set. So you often get much better results from deep learning because you've got access to all of this data and you're not relying on a human selecting the right parameters, which is often easier said than done. So throughout all this work, I'm using a simulation to create my training set and then testing it on real life experimental data. I'm not going to go into how I do the simulation of data just because of time concerns, but that was the whole body of work in itself to try and make that fast and accurate to get these large training sets. The type of machine learning architecture I use is a convolutional neural network. A lot of you probably might be familiar with these, but they've been really popular in any kind of interpretation of structured data. And a big part of the reason they're so good is they only link neighboring pixels. So by using this, you're saying there is something important about the structure of the data. So a convolutional layer, rather than connecting all of the pixels, you learn a filter that's slid across that layer to produce an output. And they've been massively successful in all sorts of things like image recognition, facial recognition, self-driving cars, image colorization, all of these sort of things, that the link is structured data. There's some relationship about pixels that are nearby, which is the same for my images. Architecture-wise, I'm not going to fully explain the architecture I use, other than to say I've designed it myself, because all the famous off-the-shelf architectures are for really high-resolution images, and also for natural images or photographs, and you can't really make the assumption that NDE data is anything like those, so I've had to design my own. But in structure, it's roughly like all of the famous ones. So I've got input plane wave imaging images, which go through repeated layers of convolution and downsampling, and this sort of convolutional section is said to do the feature extraction. And then you've got some fully connected layers at the end, which is the more of the regression task, which produces the ball loss at the end. And as I said, I train this on simulated data and I test it on experimental data. For a baseline comparison method, the most common way to do this is something called the 6 decibel drop. And this method takes an image which has an indication of defect in it. You fit a box around the top 6 decibels of that image, and then you just measure the angle and length of the longest edge. And sometimes it works really well, but it does rely on the fact that the indication is the same shape as the defect. That's not always true. So, for example, take this case, where this is a more highly angled defect. The indication of the corner is completely detached from the one of the tip, just because of the way it's angled. It's massively undersized. And this wouldn't be the case if we could transmit more plane waves. We had more information from this defect, but because of the limited data, this is what we've got. And hopefully deep learning can step in and do a better job at sizing it. So while this is a simple and physics-based approach, it's difficult to make use of more than one image, and in fact, nigh on impossible to do it in a useful way. You can also pick up artifacts rather than defects. So what I mean by artifacts is here we've got this indication, which is actually a response from a different modality. So this is a shear image, and this is actually the response from the longitudinal conversion that just shows up in the wrong place. And you can imagine a situation where this is higher amplitude and is sized incorrectly. And the big one requires the indication to be representative of the defect in size. So hopefully deep learning can step in and do a better job. So I'll look at some results. So 6 decibel drop first. We've got an error histogram here. We love all our errors to be at 0. And this is the experimental test set. But even though I'm only sizing defects from 1 to 5 mil in size, I've got a standard deviation of 1.4 mil here. So we've got some massively undersized defects. And in fact, most of them are sized pretty inaccurately. Deep learning does far better. So even if I'm training this entirely on simulated data, it does really well on the experimental data with the standard deviation of 0.63 mil. I'm super happy with these results. In fact, 79% of them are lower than a pixel size in error. The NDE familiar of you might notice I've got quite coarse images, so the resolution is half a wavelength. I have experimented with making that pixels even smaller, but while the images look prettier, it doesn't actually offer any more information because that's at the diffraction limit of what you can get out for my wavelength. So yeah, I'm really happy with these results, and we've published this in this paper here, so we can go to that to get some more details. But with the time I have remaining, I'd like to present a little bit more results of what I'm working on now. And that's the fact that if I did this test set on simulated data, it's fantastic. And that's because there are differences between simulation and experimental. You're never going to be able to simulate everything. By definition, there's going to be inaccuracies. And often you've got some experimental data hanging around, and you'd like to be able to use that in the training process. And this is what's called the domain adaptation problem, where you're primarily learning on something that's very similar to your test set, but not quite the same. And you've got a little bit of true or target data available. As I say, you've normally got a little bit of experimental data available, and there's not normally enough to, in fact, pretty much never enough to train a full deep learning network, but we'd like to be able to use it anyway. So the method I've had the most success with here is an adversarial one. What it says is that the best sizing network would be one that predicts only on features that are consistent across your simulation and your experimental data. So to do this, you train a classifier that, given some data, tells you whether it's simulated or experimental. It gets really good at doing that. And then when you train your sizing network, you maximally confuse it. And to show you the results of that, we've got the same histograms as before with the blue and the orange one. And with this new one, which only has data from 3 defects. So simulated training set is 14,343 image sets, but experimentally I've only got 108. And despite that being so small, while the histograms look quite similar, if you look at the extreme errors, they're massively reduced. We've only got a standard deviation of 0.53 now, which is a significant increase, seeing as this is only from 3 defects. And really happy with these results as well. And they scale really well. If you've got more experimental data, you're able to close this gap between accuracy on simulated and experimental data really nicely. So in conclusion, hopefully I've showed you that automated data analysis for NDE can be enabled by deep learning using these large simulated training sets, which is an accurate method for sizing. It's a fast one, so you can interpret tens of thousands of data sets every second, which is obviously significantly quicker than a human could do it. And it's an adaptable method, so if you've got some experimental data around, you can include that in the process as well. In the future, there's still one massive hurdle to tackle, and that's the fact that there's no confidence in these predictions. So I can give this network any array of numbers in the right size, and it will produce a wall loss. It'll tell me something, but not any confidence in that, which would make it really hard to use in practice. As someone trying to put this method to a company would say, okay, well, how do we know it's correct? So that's what I'm working on at the moment. And I'd also like to try it for more applications. So something like total focusing method, where you've got many more views and images. Would that produce an even more accurate sizing network? And other modalities as well. So if you've got data from electromagnetic inspection, for example. So that's it. Thank you for listening, and hopefully we've got time for some quick questions.
That's great. Thank you very much, Rich. So yes, I mean, we might have time for just 1 or 2 quick questions, but we are now overrunning, so keep them brief, please. Okay, well, while we're waiting for those to come through, I've got a question which is about sort of the scaling of this approach. So, I mean, classically, we think of deep learning approaches as quite computationally expensive. And if you're starting out with a large amount of data from these kind of pipeline inspections in the first place, I mean, at what point does it become kind of intractable? And what kind of approaches can be used to stop it becoming intractable?
I found that the key is trying to reduce the parameter space of your problem. So if you try to learn a sizing network that could size cracks, side drilled holes, any positioning of them, if you try to ask it to do too many things, you're never going to be able to learn it. So as long as you restrict yourself, and what you're then saying is, I know something about the problem. So in this case, we know that we pretty much always get cracks on the far wall, and we learn a sizing network just for that. That's fine. We can deal with the high dimensional data, and we can simulate it enough. And you can create really deep networks and have real success. But yes, if you make the challenge too wide, then you really come into issues.
Okay, great, thanks. So I've got a question here from Caroline. So Caroline asks, are you planning to apply this methodology to other ultrasonic inspection techniques like time of flight diffraction?
I probably won't have time to myself, just because this is it being an NHD, as I have a sponsor company, they're really keen to like, how does this work on our data, which is totally fair enough. So I probably won't get around to it, but I don't see any barriers to entry to any other types of data because it's completely agnostic to what it's looking at. I guess one difficulty with time of flight data is you don't have quite such simple structure to it. So when you create an image, it's like distance by distance on your axes, which is really similar to an image, right? But if you've got raw time of flight data, you've got transducers by time, right? Which is a little bit funkier. I don't know if that would work. Just have to give it a go, I guess. All of it's been a learning experience through doing, I'll say.
Yeah, great. Oh, well, thanks very much. Thanks very much, Rich. Okay, so okay, yes, Caroline says thank you. Sounds like another NHD/PhD. Yeah, definitely. Okay, well, in that case, I'd like to thank all of our speakers. And we'll wrap up there. I also want to thank James Barker from the Southwest Nuclear Hub for putting this together, and for all of you for attending. So yeah, do check out some of the websites I posted there in chat if you're interested in any of the topics discussed today. But otherwise, have a really nice afternoon, and thanks for joining us.
Thanks, everybody.
Okay.